First of all, thanks to Q2B for arranging this wonderful event over here. And I want to start by saying this is my first time in Tokyo. Being a vegetarian, I'm absolutely loving the delicious food over here. So with that, let me actually start with who we are. I don't think we have a slide on who we exactly are. So Agnostic is a quantum startup out of Toronto. We deal with software solutions for any kind of advanced computers. So today my talk is going to be on how do you orchestrate all of these large workflows that involve various kind of interesting hardware solutions that is out there on the cloud. So let me start by first speaking about the challenges that we are facing right now. So today's most important problems, as we saw in all of the talks that previously were conducted, involves high-performance computing solutions. And not just that, it also involves using a lot of advanced computing solutions like just the previous talk we had, the digital annealer from Fujitsu, for example. And most of these problems involve solving things like complex systems, understanding the dynamical behavior, solutions that you don't know exactly how to solve analytically, but you are forced to simulate it using these kind of hardwares. And of course, solutions that are extremely hard to simulate and computationally complex as well. So to give a few examples, so here is actually a interesting paper that was written by Tesla on battery simulation that involves studying strongly correlated system in lithium cobalt oxide. And here's another example of an amazing paper written by DeepMind on protein folding. And this actually involves a very state-of-the-art algorithm called AlphaFold for people familiar in the biological side. And here's another example which we actually did on trying to understand quantum simulation for portfolio optimization, where we did close to 500,000 calculations using various computing hardwares. And one thing that's common to all these three things is the requirement for solving very complex problems using computational simulations. There are actually very interesting forces that are pushing us towards thinking about heterogeneous computing and distributed computations. So let me give a few examples of the broad market forces that are pushing us towards to think about not just the kind of computation problem you can solve in a single CPU, but rather using multiple CPUs and multiple GPUs together to solve these problems. So here's a very nice graph that you see here. And this is coming in from the top 500, if you're familiar with it. That's the top 500 supercomputing centers that exist out there in the world. And here is the 500th computer and how the projected performance of it is going on. And here is the topmost supercomputer and how its performance is going on. And how here you see how everything combined together, the performance, all the 500 computers together going on is. And you kind of see a neat trend over here where things are saturating at this point. And you also see another very interesting insight over here, that when you combine all the 500 computers, supercomputing centers together, you almost get 4 times performance of the topmost supercomputer that exists out there throughout the years from 1990 to the current day quantum computers. And in fact, in one of the recent supercomputing conference that we went to, if you're familiar with it, there's a separate category of Green 500 that's called, which is like power efficient supercomputers. It turns out that if you want to go beyond the strongest, biggest supercomputers that exist out there right now, which is called the exascale supercomputers, you need to have a separate power grid close to the supercomputing center just to power up all these supercomputing hardwares. And here's another interesting 2 sets of graphs I'm going to show you about. So this is a very neat blog post from OpenAI. And this talks about how in the classical machine learning side, the performance of each of the top performing neural networks depends on the computing power across the years that we have seen in the past. So things like, which started with AlexNet requiring 10 to the power minus 2 petaflops per day, is now scaling up to close to an exponential requirement in the recent trends going to AlphaGo 0, that's by the Google, and other systems. And this is just one of the examples that exists in the classical side, where the requirement for more and more computing power, not just in a single chip, but in more of a distributed manner is required to solve a lot of interesting problems that we need to. And in the same blog post, you also see a very interesting thing that's happening. So up until 2010, there is like a clear two-era citation that you can see there where you have um, neural networks that have been that have been scaling up to a certain set of degrees based on the computing power that have been available until 2010. And then you see a very increasing sharp trend on the kind of neural network performance beyond 2010 in the last decade just because of the computing resource and the distributed nature that's now available compared to what was existing in 2010. So these kind of computing problems are now requiring, the takeaway is that they are now requiring a large-scale distributed computation that involves not just a single CPU, but going beyond a single CPU to a more clustered and distributed manner. And this is one level of heterogeneity that exists and distribution that exists. But there are other kind of heterogeneity that comes across when you typically think about advanced computing workflows. And for instance, if you're in an organization, it's typical that you have different silos of people working independently of each other to solve various problems in the same computational experiment. For instance, you might have a machine learning engineering team who think about the machine learning algorithms that they need to design to solve a particular set of problems. And you have a separate cloud engineers who set up a large-scale cloud infrastructure for the machine learning team to start solving it. And you probably also have data engineers that kind of tap into the data store, maybe a data lake that you have in. And of course, you have a bunch of data scientists who then analyze these things and visualize it. And it's a pretty complicated set of network of people that need to communicate to solve a single problem. And this is very apparent in our team as well. So I lead the research team at Agnostic, the R&D team. And whenever we have to run any large-scale simulation, I have no idea of how to set it up in say, an AWS cloud to use a GPU. But all my team cares about is, hey, I have this interesting algorithm I need to solve, but it requires a 1,000-core GPU or a 64-core CPU that needs to run for 4 days together. And we usually send it to our cloud team to set up the cloud infrastructure for it to run. And then we get back the result. And then I go back to them and say, hey, I need to change this small parameter and run it again. And then it goes on again to the cloud team. They solve it. They give it back. It's a pretty long cycle that we need to deal with inside our team. And here's like a typical example of a quantum workflow that comes in, which is driving in more kind of heterogeneity into the scientific computing environment. And most of the people will be familiar here, the kind of variation algorithm that we need to run in, where we use multiple CPUs and GPUs to talk to a quantum computer togetherly to solve a quantum machine learning optimization problem, for example. And if what the classical machine learning side is telling us is true, that means that you kind of typically need to tune your parameters and again send these things together. And you need to kind of run a long loop, which is true in our case as well. Maybe we need to try it out with the different ansatz when it comes to quantum computing. Or we may need to try it with a different input data that we need to come in. So typically, whenever you are writing a research paper or even thinking about large-scale problems, these kind of heterogeneity when it comes to hardware, especially driven by quantum, is becoming more and more apparent to us. So here is an example of an obfuscated workflow that we are actually currently working on, part of our research team. So this involves training a language, and it's an NLP problem that we are trying to solve, and where we need to train a neural network called BERT that requires a lot of CPU and GPU power to take a text data and then transform it to a vectorized format. And then we actually use various kind of cube optimizers to pick out, because it produces millions of data points, we want to pick out the right features. So we are using digital annealers and, of course, D-Waves machine to pick out certain set of problems inside of it. And then we run it in a quantum computer to try and understand if there are any anomalies that we can detect in this NLP in this space coming in. So essentially what it actually involves is, we use GPUs in the cloud that we need to do in. One of our research engineers extremely adept at having his own GPU farm set up, so he uses his on-prem GPU as well. And of course, we use quantum computers on the cloud from various providers that we want to test in, including IBM, IonQ, Xanadu, you name it. So it's a pretty complicated workflow that we need to come in. And once one of my research fellow did this entire workflow, I went back to him and said, hey, can you try it with a different ansatz or maybe a different annealing time that you want to try it in? Now he goes back and runs this entire experiment, transferring data from a bunch of Google Cloud to Azure Cloud to all of these big orchestration that he needs to do in. So this is how messy this entire workflow is. And in fact, one of the first research projects that I showed you about, which is to benchmark the portfolio optimization, where we did 500,000 calculation, was a huge problem for us to maintain all these calculations in the cloud. So this is where we actually internally build a tool called Covalent for us to help manage all of these research problems and orchestrate all of these huge scientific workflow, especially when it comes to heterogeneous computing and distributed computing like we had in. So Covalent is a workflow orchestration platform that's specifically designed for heterogeneous and distributed computing. So the key things that this Covalent answers is serverless quantum and serverless HPC. And this involves having a workflow where you need to run it on a GPU, and probably you need to cloud burst certain things from your on-prem GPU to a cloud GPU that exists on AWS. Or you might need to run a GPU along with a quantum processing machine, quantum QPU that's using IBM, but you're still waiting on a queue. You don't want to wait on a queue in a costly GPU machine while your actual calculation is not running. And so that's where this concept of serverless quantum and serverless HPC comes in, which is pretty important. And of course, distributed computation. So if you have your single workflow, which can be scaled and embarrassingly parallelized to multiple QPUs, or multiple GPUs, or even multiple CPUs, and of course, heterogeneous hardware and heterogeneous software. So few of our code is written in Fortran, C, Python, Julia, which is a big fan. All these complex experiment in a single workflow usually contains multiple things you need to run in. And that's where exactly Covalent kicks in. So Covalent unifies the hardware, software, and the language into a single scalable framework. So one of the main choices we need to make in is, we want it to be in such a way that you need to do very minimal changes to your existing code base to make it run with Covalent. And being a researcher, and a lot of the talks that previously I had in quantum is at a point where it's not production ready. Most of the workflows are research oriented, which means you need to rapidly iterate and prototype whatever things that you are working on. So one of the choices we needed to make during the architecture of the choice is that it needs to be rapidly prototypable in various kind of workflows that you need to do in. And of course, we wanted to have a very powerful visualization tools to exchange ideas between different researchers on how you want to run your workflow, what kind of things you want to communicate in between, and all those things. And one of the core principles when it comes to software design is versioning, and that's the famous products that you see there like GitLab and the entire Git framework for versioning different code bases. And we want to bring some kind of that notion to experiments as well. How do you version experiments when you're running it? How do you think about caching your experiments and all those things? So here's like the core functionality and feature list that you see here. So Covalent is purely Pythonic, which means you don't need to write text-based YAML or text-based procedures of what you need to do. You can programmatically run your workflows, which can scale up to 1,000 different parallel things to millions of parallel things that can run simultaneously. Covalent has real-time monitoring. So some of our workflows, as I said, involves running it in a HPC cluster for a couple of days together, and then transferring the data from there to an AWS cloud to do specific things on GPU. So do you want to babysit all of these things while doing it, or do you want an automatic monitoring system that does all of these things in the background? And of course, one of the things that's also important to us is reproducibility. Being a scientific person, you want to rerun your workflow and get back the same result that you had previously gotten. And of course, scaling across devices. So what that means is, typically we wanted our users to code things in their laptop, test it out, and then scale it out to the cloud, be it to thousands of GPUs or CPUs out there. Okay, so this is a bit of a technical side, but this helps a lot of people to understand where exactly we place ourselves. So about a decade or so ago, Python was introduced to parallelism. And things like joblib, Cython, Numba, PyCuda, these are all, especially by our NVIDIA guys, or things that are meant to parallelize your code to a very good extent, given a single CPU or a single GPU. Then came in a bunch of tools in Python. And the goal of these tools was to distribute your computation across various CPUs, various GPUs, and various other machines. So that's the goal of distributed computation. Now you want to take your problem, and I have 20 different laptops with me. How am I going to make my code faster when I have 20 laptops with me instead of just using a single laptop? let's just pause there and look at these set of tools here. And these set of tools are predominant in the classical machine learning side of the things in industry. So imagine Netflix, for instance. What they want to do every day is they want to look at what all the movies that you have looked at yesterday and run a machine learning model that exists on the cloud and then recommend new kind of movies that you want to watch today. And these algorithms run on the cloud every day at a given time and involves a lot of GPUs and CPUs that need to retrain your system and maintain all of these workflows. So the goal here is I need to run huge workflows every day efficiently without fail. And how do I manage it? Is there any easy way to manage it? So the game here is how do you manage workflows? And the game here is how do I make my computation faster to run? And these things are called distributed tools, and these things are called workflow managers, and we exactly sit in between them, and we call it distributed workflow. How do you distribute a very complicated workflow to multiple hardwares that are extremely heterogeneous and multiple frameworks that are extremely heterogeneous to each other? And this is exactly where Covalent sits in. Okay, not going into a lot of details over here, but imagine a pseudocode like this, where you have some kind of function where you want to, let's say, optimize, and some kind of function where you want to train using, say, TensorFlow. And you define your workflow as what you want to do, a bunch of tasks joined together, and you typically run it to get your result. With almost single line of code addition, you will get amazing features out of this, which we will see. But just pause a moment here and look at how powerful this tool is. Which means that if I want to run this particular function in an AWS cloud using 30 GPUs, without any extra code addition of a single line, I can ship this entire function to run in a 30-core CPU that exists in AWS. And if I want to run the same function in GCP, just switch the AWS to a GCP executor, and you can start running your same code without any change in a GCP. And let's say I have a local cluster in my site, which is typically if you're in an academic HPC cluster, you use job management tools like Slurm or PBS that exist out there where you can specify the number of cores or CPU you need. And you can specify that this function needs to run in my local cluster that uses Slurm executor. And what's even more powerful is that I can use all these things in the same experiment that I'm doing it in. So my single experiment can now contain things that needs to run in GCP, Azure, my local on-prem cluster, or IBM, you name it. And this is all done with a single line of code that you add on top of existing Python functions. That single line of additions, apart from giving you the powerful ability to transport your code to any kind of provider that you are having in, also gives you a very neat visual UI that you can look at. So as I said, one of the goals is that you want to do rapid prototyping and rapid iteration, which means that you want to change your ansatz and run it again. You want to change the number of layers in your machine learning algorithm and run it again. So Covalent lets you do it and looks at all the kind of project management tools you need to understand the various jobs and experiments you're running in a browser-based UI. And of course, you can visualize all your workflows that exist out there. You name it, you kind of see exactly what steps you are taking in, parameter caching, all the important checkpointing that you need to have in, looking at the details, the metadata, everything is stored completely in your workflow without you doing any effort with a single line of code, of course. So Covalent now supports a lot of software packages. We have Slurm Executor, AWS, a lot of backends that exist out there, a lot of quantum resources. We saw the amazing Qiskit runtime that exists for hybrid jobs. You can easily directly plug in Covalent inside Qiskit runtime. And we are agnostic to the kind of package that you need to use in, which means you can use any and all Python packages that exist out there. But we're also very familiar with the fact that HPC users go beyond Python and use different languages like Julia, C++, Bash, or Fortran. So we provide multi-language support to run your workflows as well. Yeah, so if you want to use Covalent, what you can do is, let your sales team contact our sales team and start. Okay, I'm just kidding. Covalent is open source. What that means is you can just use it for free out there. It exists. And there are a lot of other features that I haven't talked about, which you can, of course, come to our booth, which exists out there. And we can discuss a lot more interesting things and even contributions that's coming in out there. So this is exactly who Covalent is for. If you're doing any kind of software research or any kind of machine learning, be it classical using multiple devices that exist on the cloud or in local on-prem, and you want to scale your workflows, you can directly download our open source tool, contribute to it, and start using Covalent. With this, I thank you all.